A very good afternoon to all of you. I'm Ankita from NASSCOM. I am back with the fourth episode of the blockchain series, and today I have with me Dr. Narendra Kumar, Assistant Professor, IDRBT Hyderabad. He will speak and share his knowledge on a very intriguing piece, which is blockchain protocols and security. Two more things from my side. You can ask questions anytime during the session. Dr. Narendra will cater to them in between his presentation. And please do not forget to leave your feedback at the end to help me better my future sessions. So welcome, Dr. Narendra, and over to you.
Welcome, Ankita. Thank you to you and to NASSCOM for giving me this opportunity to share some thoughts on blockchain technology. Right. Good afternoon to all the participants, and we'll get started with the session right away. Okay. So the broad agenda for the presentation would be, I'll start with a brief introduction to blockchain technology. Although many of you may be aware and would have heard about this, this is my own perspective on blockchain technology. So I think it helps to understand before we go on to other details. And then I'll talk a little bit about some prominent blockchain protocols. And finally, we'll talk about security and privacy aspects of blockchain technology. Right, so moving on to part one, introduction to blockchain technology. Okay, so consider the following application scenario. There are multiple mutually distrusting entities that want to transact with one another. And when I say transact in this context, what I mean is exchange messages. What form that message contains and what is the meaning of the message is application specific, and we do not have to worry about it at this point of time. Okay, so multiple mutually distrusting entities want to transact with one another, which necessitates that there be a mechanism for transparent data sharing, that the records be maintained in a trustworthy manner, and in particular, all of this becomes interesting if there are interdependent transactions, which means there is a whole workflow which consists of multiple steps which have to be carried out by different entities participating in the system. Okay, but of course, the scenario that I just described is something which we come across quite often in the real world, which means we must be handling these kinds of problems somehow in practice already. So how do current systems handle such things? I would like to explain it with the help of an example of a simple fund transfer. Suppose there are two people, C1 and C2, and C1 wishes to transfer some money to C2. So the way it works is, and of course, I'm assuming for that C1 and C2 bank with different bankers, different banks, B1 and B2. Okay. So what happens is, of course, in case of physical cash transfer, C1 and C2 meet at a place, and C1 hands over the money to C2, and both of them shake hands and walk away. The transaction is done and dusted. But how do we do it in the digital space is C1 instructs his bank that such and such money has to be transferred to C2. Bank 1 records in his database D1 some information about this transaction, and whatever updates he needs to do to his local database he makes, and then forwards the request to, let's say, the trusted central party, which happens to be the Reserve Bank of India for the fund transfer use cases. So the Reserve Bank of India, as far as the Reserve Bank of India is concerned, this is a transaction between Bank 1 and Bank 2. So what the Reserve Bank of India does is, it adjusts the balances of Bank 1 and Bank 2 that it has in its system, and forwards the information to the Bank 2. Of course, it also stores certain portion of the information in its local database. And once bank 2 receives this information, it then gives a credit to his customer C2, and then the acknowledgements flow in the backward direction. Okay. So basically, to summarize, in most current systems, what happens is information about various stages of a multi-hop transaction are stored at different places, making it difficult to relate each of them with the transaction and also with one another. Okay, so this is how we solve this problem in practice today, but these are the issues that exist in today's transaction. So for example, a few years ago, if you were to convince me that you have actually transferred me some money through NEFT, you would have no way to convince me other than by giving the timestamp at which you had transferred and so on and so forth. But the problem in that case is that if I am, say, an individual receiving money, that is fine. But if I am a large organization, like for example, a school or a college, which receives fees from many students, I mean, the amounts are the same and so on and so forth. Just based on timestamp to authenticate a transaction becomes difficult. However, today that problem is alleviated by using what is known as the UTR, unique transaction record, okay, which is available at both the sender and the receiver. It's a very long string, so it is kind of difficult to next to impossible to spoof it in some sense. Okay, so if you're claiming to have done a transaction with this unique transaction record, then it better be the case that this transaction has actually happened. Okay, so now so moving on, blockchain is a term that is kind of overloaded. Many different interpretations of the word exist. In particular, it means two things. At least one thing is the data structure, and the other thing is the entire IT ecosystem that enables these trustworthy entities, mutually distrusting entities to interact and transact with one another. Okay, so we'll begin by looking at blockchain, the data structure. For those of you who are computer savvy, you know that blockchain is a linked list of blocks. Where a block is a collection of some data. What data it is, what the data means is all application dependent. And an interesting feature, linked lists have existed for a very long time. An important feature of this link is that it happens through a cryptographic mechanism called a hash, which makes it easy to verify and extremely difficult to cheat. When I say difficult to cheat, I mean computationally infeasible to reverse a hash and find another piece of data that matches the hash. Okay. Moving on. So again, blockchain is a very overloaded term with a lot of different meanings and interpretations depending on who is looking at it and from what perspective. There are so many definitions of blockchain available out there, but for the purposes of my talk, this is a definition that I have picked, which kind of maps nicely into my thought process. A blockchain is a distributed digital ledger that is used to record transactions across the participants so that the record cannot be altered retroactively without the alteration of all subsequent blocks. This is the definition that I'm going to use for blockchain. The ecosystem, it's a distributed digital ledger that is used to record transactions. So it's a whole IT stack in some sense that allows us to achieve our purpose. I think at this point, if there are any questions, I'd like to take a couple of questions before we move on.
As of now, Dr. Naren, we don't have any questions. You can proceed.
Awesome. Thank you very much. Right. And then, of course, there are various flavors in which these blockchains come. So one flavor is what I refer to as, again, there is no sanctity to this terminology, and this is not universally accepted. So this is my terminology, please understand. Public permissionless blockchains is what I refer to as systems where all the entities participating in the network can submit transactions, validate transactions, create blocks, participate in the consensus, and access the blockchain. On the other hand, obviously, if you look at the characteristics of these blockchain platforms, it becomes quite evident that this is not suitable for enterprise use cases. So people have long realized that and said, how can we use this technology in the enterprise space, and came up with what is known as a private permissioned blockchain, wherein there are designated roles assigned to entities participating in the network and 3 broad roles that are associated. Again, this is not specific to any particular platform, but this is the general structure that the private permissioned blockchains take. There are end users who can only submit transactions and access their transactions from the blockchain. There are validating peers who can only validate transactions and access their own transactions from the blockchain. And there are consensus servers that can only create blocks, which essentially means they update the blockchain and participate in the consensus process. Okay. And then I'll quickly go over some terminology. This I think most of you should be familiar with, but just for completeness, in the blockchain world, a transaction is transfer of something from one entity to another. And at a very abstract level, this something could be simply a message that one party sends to another. Genesis block is a block that contains the initial state of the system. A block is a set of valid transactions, and obviously validity is with respect to the transactions in the previous block and the state recorded up to that point of time. And blockchain, which is also known as a distributed ledger, is a backlinked sequence of blocks denoting the changes to the state of the system. Moving on, mining is the process by which a new block gets created. Fork is a situation where multiple blocks compete to be the state of the system. So for example, I'll go back to one of my earlier slides. So if you see this diagram at the bottom of the slide, so you see that, I mean, although we keep saying that blockchain is a sequence of blocks, sometimes because distributed entities with no central control are processing and creating this information, it is possible that it branches out, okay, which means there are 2 blocks that are potentially vying to be the new state of the system. So fork is a scenario where multiple blocks are competing to be the state of the system. Consensus is the process by which agreement is reached on the state of the system. See, it's important that we don't let situations like the forks exist for a very long time, because that essentially means that I mean, there is ambiguity about what is the current state of the system. So consensus is the process by which agreement is reached on the state of the system. And smart contracts are nothing but business processes translated into executable and enforceable code. Okay, right. So at this point, if there are any questions?
Yes, I have one. The question is, what is the difference between Genesis block and block? Can you explain in a diagram?
I don't think I have a diagram to explain that, but basically Genesis block is the first block that is created when the ecosystem is being set up, and Genesis block is the global knowledge that is shared by all the nodes that are participating in the system. or even those nodes which join the system later, they will be told that this is the starting point of our system, from where the whole thing has evolved. If you look at this backlinked sequence, see, the validity of a block is only when it is properly connected to its previous block, correct? So this chain can keep going backward only up to a certain finite point, and the last point to which we can reach is the genesis block, the initial state of the system where it all began. Okay, so genesis block is basically block 1 of the system, and then you can keep adding subsequent blocks to the system. So block 1, block 2, block 3. So for example, to give you an example from a real life that you can relate to, think of a blockchain as your bank passbook. Of course, nobody uses it these days, but think of a blockchain as a bank passbook. And genesis block is essentially the first page on which, the day on which you open the bank account, they say that this is the initial deposit that was made. Okay, that is what the genesis block is. Whereas every page in the passbook which contains a sequence of transactions that you have performed, ordered in a chronological manner, is what is a block. I think I'll move on. I have sufficiently answered that question, I believe. Okay, right, of course. So I'll not dwell much on this slide except to say that blockchain is very widely regarded as a disruptive technology which is capable of disrupting the very fabric of our lives, the way we communicate and the way we conduct business. I mean, of course, we are yet to realize the true potential of that, but basically these are many sectors, industry sectors, where blockchain can be used, and what are the use cases across these sectors is what is listed here. I'll share the presentation, so I think you can see this. And in India, if you're looking at the scenario, there are many states which are working on use cases, I mean, for their own state. So again, I will not discuss much here, except that the top 3 use cases seems to be land registry, farm insurance, and digital certificates in the education sector. Okay, so I'll move on. Okay, so that kind of completes our first part, which is a brief introduction to blockchain technology. We'll now move on to part 2, which is prominent blockchain protocols. One disclaimer before I proceed: there are several blockchain protocols and blockchain platforms that adopt slightly different philosophical stance available. There are several thousands of them, and it will be practically impossible to kind of summarize all of that at one place. So what I'm trying to do is pick up some representatives, in particular some systems that we have studied here at IDRBT, and I'm going to kind of dwell on some of the characteristic features of these platforms and protocols, of course. Okay, so right, so examples of public permissionless systems are Bitcoin and Ethereum, and examples of private permission systems that we're going to look at in a while are Hyperledger Fabric, Corda, multi-chain, and Quorum or enterprise Ethereum systems. Okay, so for each of these protocols, I will have 2 slides. The first slide that explains what is the structure of a network in the system and what kind of information do each of the nodes have, and the second slide which talks about how the transaction workflow happens in that system. Okay, these 2 I believe are very crucial to understanding how the system functions. Okay, so let's get going. Bitcoin, and by the way, I have taken the liberty to combine Bitcoin and Ethereum because at a level of abstraction, though there are many differences, at a level of abstraction, for my purposes, they work in exactly the same way in some sense. Okay, so what is the structure of a Bitcoin or an Ethereum system? They consist of a set of peers that are connected in a peer-to-peer network. Every peer is allowed to create and submit transactions, store and view all transactions, and participate in mining and consensus process. Okay, and how does the transaction happen in these systems? Is as follows. A transaction is created and submitted to the network. Every peer receiving the transaction validates the transaction and forwards only if it finds that the transaction is valid. This is important for security of these systems, because what it means is, if you have truly independent entities participating in the system, an incorrect piece of information will not get propagated more than one step. Okay, the peers participating in the mining process create and publish a new block that includes the transaction, and this mining typically is represented as POX, which could be proof of work, proof of stake, proof of authority, or any of the other alternate mechanisms that are available out there. Can you just excuse me for 1 second? I'll be back. Right. So I was saying that peers participating in the mining process create and publish a new block that includes the transaction. And by the way, I'm not saying that this will happen immediately, but this will happen eventually. And then every peer that receives a new block validates it and forwards it to other peers if it is found to be valid. A valid blockchain is arrived by consensus. So one important thing to note in public blockchains is that when we say consensus, there is technically no explicit consensus that is happening between parties. So two nodes are not discussing and saying, hey, this is my blockchain, is this also your blockchain, and so on and so forth. Based on the set of blocks they have received so far from the network, they chain these blocks up, and whatever is the largest chain, for example, whatever is the longest chain, for example, will be treated as the main primary chain in some sense. Okay, so again, the algorithms to decide which is the main chain can vary slightly from system to system. Right. Are there any questions?
Yes, we have. One question is, what kind of calculations are done in the systems while using sequence of transactions?
Sorry, can you repeat the question?
What kind of calculations are done in the systems using sequence of transactions?
Nothing. So basically, the job of a miner is to create valid transactions, and when he has sufficiently many, create a new block, which includes solving a cryptographic challenge, wherein he has to. This is, by the way, only for proof of work, wherein they'll have to generate a random number whose hash satisfies certain criteria. And once you found such a number, you include the hash of the previous block to say that this is what I am extending, create the hash of the current block, and say that this is the new block. Any other question?
That's it, Dr. Naren.
Sure, let's proceed then. Right, so that is about Ethereum and Bitcoin systems. Now let us see how the Hyperledger Fabric system works. So what is the structure of a Hyperledger Fabric system? It consists of an ordering service and a collection of channels. Each channel consists of a set of peers, which could be into three different categories: endorsing peers and committing peers. Endorsing peers are responsible for validating the transactions, and committing peers are responsible for updating the state resulting from executing valid transactions. All the peers share the blockchain that consists of all the transactions that are happening within the channel. Okay, so it's like within the channel you're running a public blockchain, but you can have many such blockchains running in parallel depending on what business you're conducting with different entities. And a node can participate in multiple channels simultaneously. Okay, each channel will have its own blockchain that is visible to only those members who are within the channel. So privacy in the Hyperledger Fabric system is limited to within the channel. Limited accessibility within the channel. If between two channels there is zero visibility, which means there is complete privacy. And how does a transaction happen in Hyperledger Fabric? A transaction proposal is created by the party who wants to make this transaction, and the proposal is sent to the endorsing peers. Endorsing peers execute smart contracts to validate the transaction and to generate the result set. Endorsed transaction proposals are then sent to the ordering service for creating blocks. Ordering service creates blocks of endorsed transactions and shares them with all the peers. Committing peers then update the state using the result sets of the transactions in the new block. So basically what is happening here is that if I want to do a transaction, I create a proposal and I send it to endorsing peers. This is like a transaction validation mechanism. Endorsing peers execute smart contracts that encode the business logic of how to process such transactions, and it validates the transaction and generates the result set. Result set essentially captures if this transaction were successfully executed, then what will be the resulting state of the system. Okay, so once the transactions are endorsed, after collecting a sufficient number of endorsements, a transaction proposal is sent to the ordering service, which is responsible for creating blocks of valid transactions. And once the ordering service creates a new block, it shares the block with all the peers in the channel. Okay, and within the channel, as we discussed, there are special people called as committing peers who are responsible for executing the transactions which are present in the new block and updating the state of the system. Okay, that is how the Hyperledger Fabric system works. Right, next we will move on to Corda system. What is the structure of a Corda system? A Corda system consists of nodes, each of which has a private state stored in the form of state objects. State objects are indivisible and have to be consumed at once. For those of you familiar with the Bitcoin system, this concept is similar to UTXO, unspent transaction output, which enables chaining of transactions with one another, which means you can have an entire history track of how an object, state object, has evolved, and this in turn leads to greater guarantees on provenance of information. Corda maintains a distributed ledger consisting of transaction chains and does not as such have a blockchain. But then the reason we are discussing Corda within this framework is because it leverages several principles. It adopts several principles from the blockchain systems and builds a distributed ledger wherein complete privacy is maintained. Okay, and then how does the transaction take place in the Corda system? A transaction is formed using signed state objects that are input by the respective stakeholders. That is, suppose you and I wish to do a transaction. Both of us say that, okay, this is what I contribute, this is what I contribute, and obviously all this is happening in the digital space. So to really know that you are interested in contributing, you'll have to put a signature saying that I am willing to put this input into the system. Okay. So once we have given these inputs, both of us execute smart contracts to check whether what happens if I put these two inputs and perform a transaction. And we get the output state saying that if this transaction happens, this is the resulting state, which means you get this, I get this. Okay. And once that is done, and the whole transaction consisting of our respective inputs signed by us and the fact that we agree that if this business logic executes, this will be the resulting final state. That whole thing is signed and it is sent to a service called as notary. Notary in Corda can be thought of as similar to the role of ordering service in the Hyperledger Fabric system. What the notary does, a notary is also referred to as uniqueness service. Notary validates that the input state objects are unspent and it checks the signatures on the input state objects and makes sure that the signatures tally, and then it marks these input states as spent, which means their owners can no longer spend these inputs, and it also records the output state objects as newly created UTXOs, unspent transaction outputs. And then the notary service puts a signature around this transaction to say that I have noted that the input state objects are consumed and the output state objects are generated. And once you and I receive this information from the notary that it has updated, it has validated the transaction, then both of us update our state. Okay. At this point, if there are any questions, I would like to take.
Yeah, one question by Dinesh is asking: are there some note playing two different role at different point of time? Dinesh, could you please repeat your question? Doesn't make a sentence to me.
No, I think I get the question basically.
All right.
So I think what he's trying to ask is whether it is possible that the same physical node play different roles at different times. The answer is kind of yes and no. Because a normal node cannot become a notary or an orderer. Those are designated roles only certain people can play. I mean, only certain nodes can play. However, two organizations can share a node and say that both our instead of having instead of each of them maintaining their own server, they can maintain one server and say that that acts on behalf of both of us. That is possible. So when it is doing transactions of first organization, it acts as their server. When it is doing transactions of another organization, it acts as the second organization's server.
That's it, Dr. Naren, from my end.
So that answers his question. Is he satisfied?
Yes.
Oh, great. Okay, so we'll move on. The next system we are going to look at is multi-chain. Yeah, so multi-chain is a permissioned version of permissioned blockchain built on top of the Bitcoin code, and Quorum and Enterprise Ethereum are permissioned systems built on top of the Ethereum system. So as I said, although Bitcoin and Ethereum are two different systems, at the level of my abstraction, the content I want to convey, they operate fairly similarly. So I will combine them and talk about how they behave, how they look like. So a multi-chain or quorum system is a collection of peers, each of which stores two things. One is a public blockchain and a set of private states. Public blockchain consists of the summaries of all the transactions that have taken place in the system. Private state contains the complete details of the transactions in which the peer was a stakeholder. So basically you can think of this as, see, if you look at the Corda system, this is completely private. A transaction between you and me, only both of us see, nobody else sees. In a Hyperledger Fabric system, all the members present on the channel see the transaction. Okay, so this is a graded increase of privacy, if you like, where we started with the Bitcoin Ethereum systems where there is no privacy. All information, where there is no built-in privacy, you can build other application layer aspects to protect privacy. That is a different story. So as it stands, there is no inbuilt privacy in Bitcoin and Ethereum. When we moved, so everybody in the world, everybody participating in these systems is able to see your transactions. When you move to Hyperledger Fabric, only people within the channel are able to see your transactions, not people outside the channel. And when you move to Corda, only the people who are participating in that particular transaction can see the transaction, nobody else can see the transaction. Multi-chain and Quorum actually take a mixed approach. They say that a summary of all the transactions that are happening in the entire network must be made available to everybody in the network. However, what the details of those transactions are can be kept private to only those parties who are participating in the transaction. Okay, so in that sense, public blockchain consists of the summaries of all the transactions in the system, and private state contains the details of the transaction, such as who was the other party with whom I transacted, what was the transaction about, was it a fund transfer, was it buying of some goods and services, and so on and so forth. Okay, right. So how does a transaction take place in multi-chain or a quorum system? To begin with, again, just like in Corda, the parties of the transaction privately agree on the details of the transaction. When I say privately agree, what I mean is they don't go through the peer-to-peer network. They establish a point-to-point connection and agree on the details of the transaction. And both of them prepare a summary of the transaction and share it to all the peers in the system. So this summary is dissipated in the system using the peer-to-peer mechanism. Predefined trusted peers participate in consensus process to create blocks of transaction summaries. So who are trusted peers is defined differently in multi-chain and quorum. I'll not go into details, but I just wanted to highlight the fact that there is a notion of predefined trusted peers that is defined in both these systems. So upon receiving excuse me. So upon receiving a new block, peers update their state by committing the transactions in it. Of course, if I am not a part of a transaction, I will only see the transaction summary, but I will not be able to make head or tail of it. Only for those transactions in which I had participated, I will have more details about the transaction, and only such people will be able to execute the transaction. Others will just ignore the summary of a transaction in which they have not participated directly, that is. Okay. Any questions here?
Dr. Naren, so far we are good. No questions.
Great. Right. So, as I said, there are thousands and thousands of platforms and protocols with slight variations and so on and so forth. So now the question is, if there is such a lot of variety available out there, there are two important questions that come to mind. Question number one is, how do I compare two different platforms? And question number two is, if I have a use case, which platform to use? How do I choose a suitable platform for my use case becomes another important question. Okay. So to answer these questions, of course, there is no 100% accurate answer. To answer this question to the best of our ability, we have identified certain common aspects that underlie all the blockchains, which are the core aspects of blockchains basically. So certain questions that are common to all blockchains are, who can create transactions? Who can view transactions? Who can validate transactions? Who can create a block? Who will participate in the consensus? And who can view the contents of a block? Okay, so these are some important questions in the context of blockchain. Now, using these kind of parameters, we will see how we can do a comparison of the platforms that we have studied. So for example, in the Bitcoin and Ethereum case, the answer to all the questions is everybody who is participating in the system can do all of those activities. Whereas when we move to Hyperledger Fabric, who can create a transaction? Basically, everybody can create a transaction. Who can view a transaction? Only those people who are also present in the same channel can view a transaction. Who can validate a transaction? Those people who are assigned the role of an endorser within the channel can view the transaction, can validate the transaction. Who creates a block? Orderer creates the block. And who participates in the consensus? Orderer to an extent. I mean, orderer participates in the consensus in the sense that he has to give the transaction some sequence numbers, and as far as the state update is concerned, it is the committing peers that participate in the consensus. And finally, who can view the contents of a block? All the members participating in the channel can view the contents of the block. Now, in the Corda system, again, anybody can create a transaction. Who can view the contents of a transaction? Only the 2 or 3 participants that are participating in the transaction can view the details of the transaction, and only those 2 people can validate the transaction, and only a notary can create a block, and both notary and participants can participate in the consensus process. Again, just like in the Hyperledger Fabric case, notary can participate in the consensus of whether a transaction, whether all the inputs are valid or not, and the participants themselves validate the fact that given these inputs, these are the valid outputs that come out of the transaction. And finally, Who can view the contents of the block? I mean, technically there is no notion of a block in Corda. It is only the participants that can see the values of the transactions. And finally, in multi-chain and or quorum systems, who can create a transaction? Everybody. Who can view the transaction? In multi-chain, everybody can view the transaction. In quorum, only the participants can view the transaction. In who can validate a transaction? Only the participants can validate the transaction. Who can create blocks? The so-called trusted entities that are participating in the mining process. And again, who can participate in the consensus? Both miners and or participants. And who can view the contents of a block? Everybody in the system can view the contents of the block. Now, this is, as I said, a brief summary of some of the existing platforms and what kind of a philosophical stand they take in terms of what blockchain is, what levels of privacy are required, and so on and so forth. Now, it may so happen that for your particular use case, none of these characteristics are good enough, and you want some other combination in which you want to handle these questions that are listed on this page. In which case, what you will do is go ahead and create your own blockchain platform. But before you decide to create your own blockchain platform, you must be aware of certain scientific results that already exist that impose certain stringent conditions or constraints on such blockchain platforms. So two of those I will describe briefly. The first trade-off is what is called as consistency versus latency, which is essentially as follows. So let's assume that there is some event happening and two of us are taking notes simultaneously, because there is a lot that is happening and one person cannot plausibly capture all the information of the discussions that are happening. So let us say two of us decide to take down notes. Obviously, if two of us decide to take down notes, I may focus on certain aspects, you may focus on certain aspects. It becomes important that both of us reconcile from time to time at periodic intervals, and that we come to an agreement on what has actually been discussed so far. Okay, if we consider this simple example of a use case or a scenario, what I mean by consistency is that both of our nodes exactly match. And what I mean by latency is that whenever somebody asks a question, we will immediately respond. Okay, I mean, or within a very short duration, both of us will give him an answer. And consistency says that our answers will exactly match. You can think through. The point is, if you want to, I mean, if two, I mean, I'm just giving an example with two people, but now imagine multiple people doing this. There is a lot of coordination that is required between these people who are taking down notes to say that all of us better be on the same page. So during that time when they are synchronizing with one another, they will not be able to provide you exact answers. Okay, and in many business and real life use cases, knowing the correct answer is kind of very important, even if it means we'll have to wait that bit longer. Therefore, this is a trade-off that can never be solved, and it will kind of exist forever in some sense. Okay, and the second trade-off is you cannot have both privacy and trusted flexible interoperability. What does privacy mean? Privacy means that others should not be able to know of my transactions. At the same time, I must be freely able to transact with many people. If I tell you that I am selling Agra, you would laugh at me, right? Obviously, because you know that I don't own Agra. So, but I mean, in a similar spirit, when I say privacy, what I mean is that at the time when we started to do a transaction, you would not know whether I actually own an object that I'm trying to sell you or not. You need some guarantee on that. So the point is, you cannot achieve both privacy and trusted flexible interoperability at the same time. There is a trade-off which you need to be aware of. So summarizing this second part of the talk, what we have seen is how different blockchain platforms operate at a broad level, and then we have seen how they can, what are the parameters based on which these platforms can be compared, and finally we have seen if for some reason you decide to build your own blockchain platform, what are some bottlenecks that you will hit sooner or later. Time for a question or two if there are any.
Yes, Dr. Naresh, question. Does Corda
Yes.
follows Byzantine fault tolerance algorithm? If yes, is it reliable if only participants are part of validation?
Uh, Interesting question. So here is my take on that. I am not very certain whether the current implementations of Corda give you a Byzantine fault tolerant behavior, although their system is not restrictive, and if someone were to implement a Byzantine fault tolerance notary service and also for each individual node, I think the systems will become more robust. I am at this point of time, with my limited knowledge, unaware of any such implementations. So the second part of the question, I'll not be able to answer whether it is reliable and so on and so forth.
All right.
And by the way, Byzantine fault tolerance is not just about validating a transaction, it's about the entire life cycle. From the time the transaction is taken up till the time the transaction is executed and the result properly stored in the system across all copies. Yes, if there is a second question.
That's it, Dr. Narendra, as of now.
Great. So we'll then quickly move on to the last part of my presentation, which is quite short, so I think will be good. And the part 3 of my presentation is on blockchain security and privacy aspects. Well, we hear a lot of talk that blockchains are impenetrable, immutable, whatnot, right? With all due respects, what I urge all of you to understand is that each of these terms have a specific technical meaning, and however, different people tend to use these words in slightly different context within their own setup. So please be mindful of the sense in which each of these terms are being used when somebody describes blockchain platforms. In the true sense, I don't think nothing on this earth is immutable. Everything changes. Change is the only constant. However, yes, blockchains, if correctly implemented, are pretty, I mean, can be pretty robust. However, despite a lot of effort going in, we still see a lot of security issues in blockchains, and some of these have practically, some of these attacks have practically happened. We've collected this information from a 2015 article that talks about attacks on blockchain systems. Particularly at that point of time, they were focusing on public permissionless blockchain systems. Okay, so some of the broad categories of attacks that can happen are double spending threats, mining pool threats, wallet threats, and network threats. Okay. So within the double spending threats, there is 51% hash power attack, which is also known as the gold finger attack. Race attacks are possible. Alternative history attacks are possible. And within the mining or pool threats, there is a problem of selfish mining, where you actually keep mining blocks, but you don't convey it to the rest of the world that I have created this block. Okay. And then there is a block discard attack, block withholding attack, and a pool hopping attack. Okay. And as far as wallet threats are concerned, vulnerable signatures, lack of control in address creation, flawed key generation, and there are network threats in the form of DDoS attacks, transaction malleability attack, and partition routing attack. Finally, as far as privacy is concerned, data privacy is at two levels. It could apply to transaction data, or it could apply to the block contents itself. And importantly, there is a identity privacy. You don't want to know who you don't want others to know that you are a partner of a transaction. So it could be on participants of a transaction and transactions that have been carried out by a participant himself. Okay. Finally, while the blockchain world is grappling with these issues, there are several advanced scientific tools that are available to help them become more secure. Some of the examples include trusted execution environments. These could come in the form of software or hardware. Example of a hardware trusted execution environment is the Intel SGX protection mechanism called the enclaves, or the software mechanisms such as containers and dockers, which are lightweight virtualization systems. And the other advanced tools include fully homomorphic encryption and zero knowledge proofs. Some of these concepts have been used in the blockchain world. However, there seems to be some issues with the implementation. For example, this zero knowledge proof system called ZK Snarks has been implemented in the Quorum system, Quorum blockchain system, and recently it was revealed that because of a programming flaw, the system is prone to errors. Fortunately, nobody had detected that flaw and kind of took undue advantage of this. Before somebody could do that, these people could figure out that flaw and fix it. Okay, so I think this is where I close. This is what I wanted to share on blockchain technology. What are the different protocols, how they work, and what are the security and privacy concerns that you should be aware of. And for those of you interested in solving problems, these also give you a hint of what kind of problems exist for you to solve them. Okay, thanks for your attention. If there are any questions, of course, I'll be happy to answer.
As of Dr. Naren, no questions so far. So let's just wait for a minute. We have 2 more minutes to close the session.
Sure.
Yeah. Any questions so far? There's one question. Can you please take question from her? There is yeah. How data integrity involved in blockchain system?
Sorry, the question has to be a little more specific. I think it is vague at this point of time.
All right.
So repeat the question. I'll try to see what I can answer?
How data integrity involved in implementations to be possible?
No, I'm really sorry. The only meaningful question that I can make out of it is how blockchains ensure data integrity, or how can we implement blockchains and make sure that we have high integrity of data. Well, again, there is nothing like absolute perfect data integrity. The best we can do is two things. One is you have high fault tolerance, highly available service, which means you'll also pay some cost in the form of delayed responses, slightly more delayed responses, depends on how much replication you want to have. And secondly, although many of these concepts are perfect in theory, when it comes to implementation, there are typically some problems because of which, I mean, bugs because of which you don't really get that level of data integrity as promised in theory. That is my reading of the question. I could be wrong. Sorry.
All right, there's one more concerning governance. Do you find any more areas where implementations are possible or to be possible?
See, the way I look at blockchain technology is basically as follows. To me, the greatest innovation that blockchain has brought about is the possibility through a technology platform of many people looking at the same copy of the data, which in particular solves a problem of end-to-end security in distributed systems. Many problems occur in workflows in real life because not all participants have the same understanding of what is happening in the system. So governance in particular possibly requires greater collaboration and I would say visibility into the same data, so that we don't waste efforts in repeating the same efforts that somebody else is already putting in. And for example, tracking of many of these schemes by the government, etc. All these use cases, I believe some level of transparency, traceability, and accountability can be achieved in governance use cases.
All right. Looking at the time, let's have a last question, Dr. Narendra, before we close this session. The last question is: do you forecast any new technologies in the near future which could compete with blockchain technology?
Difficult question. Difficult question. Not really. See, honestly speaking, all of these technologies that we have today have been known in science for a very long time. It's just that they're getting traction because of complex real life use cases that we find these days. So I don't think I'll be able to answer that question. What new technologies do I foresee to be competing with blockchain going forward? Blockchain has some nice characteristics, and we should not think in terms of competitions, rather think in terms of collaborations. Blockchain will become an integral part, like just like AI/ML, for example, and cybersecurity, for example. So these technologies will have to be used in tandem to achieve a greater purpose.
All right. Thank you, Dr. Narendra, for
Yeah,
this answer. And thank you so much for this enriching session and all the details you shared in your presentation. Truly a learning session it was, a webinar. And
sure.
thank you for your time and
And
efforts.
right, I would like to receive feedback.
Sure, sure. Tomorrow I'll be sharing the feedback stats with you, Dr. Narendra. And to all the
Great.
other audience, I will see all of you on 8th of August on the topic How to Crack Product Management from the Product Management series. Thank you, everyone, and thank you, Dr. Narendra, especially for your time and efforts.
Absolutely. Thank you very much. Thanks for this opportunity to NASSCOM. Thank you very much.
Thank you. Thank you, all of you.